Two-dimensional autonomous systems refers, the first portion here is in relation to the dimension of the dimension has to do with the number of state variables. Okay, so here we're going to work with x1 and x2. This we can consider this a vector of state variables, if you will, and the two-dimensional systems that we are going to consider now look like this, right? So we consider a matrix of entries denoted here as A11, A12 for entries on the first row, and A21, A22 on the second row. In general, we're really considering the derivative of the state variable vector x versus time. So we're assuming that x as a state variable vector is a function of time t, and that its derivative is simply a matrix column vector product that we can write as A times x. Very importantly, we're going to use the notation lambda and v with index 1 and 2. So we write A times v sub k equals lambda k vk. This means that we have eigenvalue lambda 1 with eigenvector v1, corresponding eigenvector, and then we have lambda 2, eigenvalue lambda 2 with corresponding eigenvector v2. So the general solution is a linear combination of eigenvectors. It's something that in this case would look like this. It's simply a sum with two terms. We have lambda 1 exponential e to the lambda 1t. That's a scalar and multiplies the vector v1, which is the eigenvector corresponding to lambda 1, and similar for the second term. So let's remember that in general we can write a complex number with the representation alpha plus I beta. So in this case, what we're saying is that the real part of lambda k is equal to alpha, is denoted with alpha, and then the imaginary part, the so-called imaginary part of lambda k here, is denoted with beta. If that is the case, then lambda k times t takes the form alpha t plus I beta t, and what we'd like to do next is to have an expression for e to the lambda k t. So we'd have to exponentiate that e to the lambda k t, which means that we're exponentiating alpha t plus I beta t. Right? We can take the exponential of this, and by an application of Euler's formula, this exponential of lambda kt is now split, basically has the contribution of an exponential that involves the real part of the eigenvalue and a linear combination, if you will, of the functions cosine and sine, such that the argument of these functions involves the imaginary part of these eigenvalues. This expression is coming back. It's something that's not entirely new in the context of differential equations, but it's simply kind of a reminder. Very importantly, from this calculation we can make a conclusion directly, and is that when the real part of the eigenvalues is negative, then that means that this term e to the alpha t is going to dominate the entire product. In other words, the function of time e to the lambda kt is dominated by exponential decay. As you can see here, that if alpha is negative, if the real part is negative, as t increases in value, then e to the lambda kt will decay to 0. Right? So you're basically making the conclusion that this portion, e to the alpha t, having alpha being a negative number, when t takes positive values increasingly larger, then that's gonna behave. That's you need to picture this as a function of t, and that exponential function is something that's decaying to 0. This would be e to the alpha t. This is for alpha negative. But it's also important to keep in mind that e to the lambda kt also receives contributions from the cosine and sine functions, and that under other circumstances it may be the case that the periodic or oscillatory behavior of cosine and sine may be more direct contributions to this function e to the lambda kt. So if we are in summary, if we're interested in computing the solution of this linear system with initial conditions, another name for this is initial value problem, the first thing that we do is to write the system in matrix vector form and then compute the eigenvalues and eigenvectors for this system. That will be computing lambda, the lambdas and the v's, its corresponding eigenvectors. Then we can write the initial conditions as a linear combination of the eigenvectors. If we evaluate at 0, the exponential parts will vanish, and we have something that looks like c1 v1 plus c2 v2. And what we need is to solve for those constants c1, c2, given the initial conditions. We'll multiply each eigenvector by e to the lambda kt. We multiply v sub k, and then write down the general solution in this form. So let's now use that method, and we want to illustrate that method with this exercise. Okay, and so the first thing that I would like to note here is that this system of equations, x1 minus 2 x2 and 2 x1 plus 1 x2, we could write this vector as the product of a 2 by 2 matrix times a column vector that has entries x1 and x2. So what we're looking is collecting the coefficients. We look at that expression. This would be 1 x1 minus 2 x2. So in the first row we write 1 and minus 2. On the second row we write 2 and positive 1. So you can rewrite this system as something that looks like derivative with respect to time of vector x1 x2 equal to a matrix vector product where the vector has x entries x1 x2, the vector state variables, and the matrix is 1 minus 2 and 2 1. Okay, so that's the first step, is to rewrite the equations in matrix vector form. So here the vector of initial conditions has values 8 and 2i. So you may wonder here that even though this system has entries that are real numbers or complex numbers with 0 imaginary parts, the initial conditions are given. This is for t equals 0. They're evaluated at 0. Their initial conditions are given involving an expression there with a complex value. But that's okay. We'll get to that in a minute. So we need to compute the eigenvalues of this matrix. And to do that, we compute first the characteristic polynomial, which means that we're computing the determinant of this matrix now involving, we're going to use the lambda as the variable of the polynomial. So this computation is reducing now to 1 minus lambda squared plus 4 and this quadratic polynomial can be written as lambda squared minus 2 lambda plus 5. So what we would like to do is to find the roots of this quadratic polynomial, and so therefore we're going to have that the roots we're interested in, which are the lambda 1, lambda 2, comma lambda 2, these roots are going to result from the calculation that looks like 2 plus minus. So inside the square root, we'll have the square of minus 2 minus 4 times 1 times 5. That square of negative 2 is going to be 4, and we'll have basically here 4 minus 20. So inside the square root, we're going to have a negative 16, and this would lead to an expression that looks like 2 plus minus square root of negative 1 is going to be I times square root of 16 is going to be 4, and everything here will be divided by 2. So we are obtaining that the eigenvalues will be 1 plus minus 2i. So now we have to decide which one we name lambda 1 and which one we're going to name lambda 2. But very importantly, we need to establish what are the corresponding eigenvectors. So we can compute the eigenvectors from using reduced row echelon form and calculation of a basis of the null space. But suppose we use something like CoCalc or SageMath, and then we obtain information that one of the eigenvectors is going to have the form 1i. So now we need to establish if this vector corresponds to one of those values, which is the roots, each of those values, 1 plus minus 2i, each of those values is a root of this characteristic polynomial. So to do that, we multiply the matrix times this vector. And so remember, one way of doing this matrix multiplication is doing the linear combination of the columns. So the columns are 1, 2, and minus 2, 1. And here we have entry 1, and here we have the entry I. So this becomes 1, 2 for the first column plus minus 2i, and I for the second column, and this leads to the vector 1 minus 2i and 2 plus 1i. Okay, so what we'll do next is to multiply both of those scalars times this vector with entries 1i. Okay, so we're going to multiply the scalar 1 plus 2i times this vector, and so this would give us another vector that has entries. First entry is 1 plus 2i, and the second entry would be I plus 2i squared. This means that the first entry stays as is, 1 plus 2i. The second entry becomes minus 2 plus 1i. Okay, so what we're looking for is if there is a match, right? And if we compare the first entry of this vector, this entry, with the first entry of the previous vector we computed, then we can see that there is not a match. So let's be hopeful and carry out the second calculation. We multiply 1 minus 2i times 1, that gives us 1 minus 2i. And we multiply this times I, that gives us I minus 2i squared. And so this would give expression we're looking for. The real part would be positive 2 plus 1i, and in the first entry we have 1 minus 2i. So we can compare here the first entry of this vector is a match, and the second entry being 2 plus 1i is also a match. So we would say that this vector 1i is going to be the eigen vector that corresponds to that corresponds to 1 minus 2i. So we're going to call this lambda 2, and this vector, its corresponding eigenvector, v sub 2. Lambda 2 is 1 minus 2i, v sub 2 is 1i.